problem number 2 on the 454649 test review is our optimization problem. It says a drinking cup is made in the shape of a right circular cylinder with an open top, right? A cup with an open top. For a fixed volume of 30 inches cubed, we wish to make the surface area as small as possible. What is the height, radius, and surface area of the cup? Show your work. Well, I am going to start by drawing a picture of what my cup would look like. So I know that it is a right circular cylinder. So here's my cup, and it has an open top. So obviously this cylinder has some height of h, and it has some radius of r, okay? And they tell me that they want us to make the surface area as small as possible. So we know that we are going to have to work with the surface area of a cylinder equation, right? And our particular cylinder has a bottom, but it does not have a top. So we know that we're going to have the area of the bottom of this cylinder, which is a circle, right? So here's my surface area equation. I'm just going to write it down. The area of the bottom of the cup is going to be pi r squared. And then we have the cylinder part of the cup, right? The sides are the cylinder part. Now, if we were to roll that out, right? If we were to like slice down the side of the cup and unfold it, that is actually a rectangle, right? So if we think about that, this part of the cup is the circle and that part of the cup is the rectangle. And the rectangle has an area, and again, maybe I'll draw it over here, right? The height of the rectangle would be h, and then if we unfolded that, like unfolded it, then the circumference of the circle would be the length of the rectangle, which we know that the circumference of the circle is 2 times pi times r. So our sides of our drinking glass, or the surface area of the side wall that is the cylinder shape, is going to be 2 pi r times h, right, times the height. So there's my surface area equation for my cup. The other information that they give me in this problem is that the cup has to have a volume of 30 inches cubed. So I would like probably to use the volume of a cylinder equation, which if you don't know the equation for volume of a cylinder, you could look it up. Volume of a cylinder is equal to pi times radius squared times height. Okay, so here is our issue. Our surface area equation, which we are trying to minimize, has too many variables in it, right? It has both radius and it has height in it. And our volume equation has both radius and height. So what we can do is we can do a substitution for h in the surface area equation using our volume equation. So I am going to solve the volume equation for h. So right now I'm going to divide both sides here by pi r squared. So then I get h is equal to v over pi r squared. And now I am going to substitute that into my surface area equation for for h, so that I have a surface area equation that is only in terms of r. So I only have it in terms of one variable, because that's my goal. I want it one variable so that I can take the derivative of it, right? So now my surface area is going to be equal to pi times radius squared plus 2 times pi times radius, and then for height, I'm substituting v, which, sorry, I should put v is 30, right? So 30 over pi r squared. And then I can do some simplifying. So my surface area equation will be pi times radius squared plus 2 times 30, all in my numerator, is going to make 60. Still have my pi. Oh, actually I don't. Over here, the pi and the pi will cancel. And then I have r over r squared. So this term is just going to become 60 over r when I simplify that. So that's a much simpler equation there for my surface area. Okay, so now I am trying to minimize my surface area. So this is the point where I am going to take the derivative of my surface area to find the critical values. So use the derivative of surface area to find critical values. So my surface area prime is going to be equal to, remember pi is just a number, so that's a coefficient on r squared. So if I bring down the 2, this just will be 2 pi r. And then my second term, when I take the derivative of it, right now r is in the denominator, so it has a -1 power. So if I bring down the -1, that will make my term -60 r to the -2, which I will write as r squared in the denominator. Okay, so here is my equation. Now I'm going to have to do some algebra when I set this equal to 0 to get my critical values. So I have 0 equals 2 pi r minus 60 over r squared. So if I'm trying to solve for r, I'm going to add that 60 over r squared term over to the other side. So then I'm going to have 60 over r squared is equal to 2 pi r. And then if I want to get that r squared out of my denominator, I am going to multiply both sides of the equation by r squared. So I will have 60 equals 2 pi r cubed. Now, of course, I can divide both sides by 2 pi to get my r cubed alone. 60 divided by 2 is going to be 30. So I'm going to have r cubed is equal to 30 over pi, whatever that value is, right? Because pi is a decimal, so that's not going to be a nice number. But when I take the cube root of both sides to solve for r, right? So I'm going to cube root the left, and I'm going to cube root the right. I get r is equal to, and the cube root of 30 divided by pi, rounded to 3 places past the decimal, is 2.122. Okay, so now I want to make sure that this is actually a minimum for my first derivative, right? Because I am trying to make my surface area as small as possible, right? And I probably should have written this down in the beginning. I want to minimize my surface area. So I want to verify that r equals 2.122 is indeed a minimum. So I am going to use the first derivative test for that. So here's my number line. Here's my 2.122. So I'm going to test something that is smaller than 2.122. How about if I just use 2? And I'm going to test something that is larger than 2.122. It doesn't matter. How about if I use 2.2, right? Just keeping the numbers really close to 2. And again, I am plugging these into my first derivative equation, which is going to be this equation right here. So I'm certainly going to just type this in on my calculator, right? Because these aren't nice numbers. I've got pi, which is a decimal, and I've got, the 2.2, which is also a decimal. So when I plug positive 2 in, 2 times pi times 2, and then minus 60 over 2 squared, that is going to give me a negative value. And when I plug 2.2 in, okay, then pi times 2.2 squared, and then negative 60 divided by 2.2 squared, that is going to give me a positive value. So since I have a sign change here, this proves that 2.122 is indeed a minimum. Okay? And so now that I know that, the radius that is going to give me the smallest surface area possible is going to be 2.122. So this is part of my solution. But I was also asked to find the height and the surface area. Well, I have an equation for height. height was equal to the volume divided by pi r squared. So I will just plug my 30 in for volume, and I will plug my 2.122 in for radius, and grab my calculator. And when I type that in, I get that my height is equal to 2.121. So that is the height that is going to give me the minimum surface area. And then finally, what would the surface area of this cup be? Well, I just need to plug my R and my H into my surface area equation. So my surface area is going to be equal to pi times 2.122, that's my radius, squared, plus 60 divided by my radius, which is 2.122. I'm using the equation where I actually simplified and eliminated height. And so then I get my surface area is equal to 42.421. And this is going to be units of inches squared. My height, sorry, I should have put labels on here. My height is in inches and my radius is in inches as well. And you certainly could have plugged your radius and your height back into the original surface area equation, pi r squared plus 2 pi r h, and you would have gotten the same value for surface area. So just to make sure we've completely answered the question was, what is the height, radius, and surface area of the cup with minimum volume? And we have provided the radius. That's what we found. That's, what we optimized, right, to find the minimum. And then using that radius, we found the height and we found the surface area by plugging that value back into equations that we had already created within the problem.